Hello, welcome to yet another exam review. So here we want to take another look at second order systems, just because they're tricky like that, and we want to look at the second order parameters. We won't bother to do homogeneous particular solutions here. We just want to look at the parameters associated with second order systems. So what I'll do is write kind of a messy looking, I don't know. Let's get really messy. So let's say you've got a system that looks like this. Now, in a design scenario, A, B, and C might be physical parameters, like, for example, the diameter of a shaft might influence its mass, or the size of a gap in a rotating system might influence the amount of drag on it, which would give you a damping term that might look like this. And this c squared, this could have something to do with the cross section of something could vary its thickness, right, or vary its stiffness, excuse me. And so you could imagine messy looking equations with these coefficients in them, right? And so we might be left to choose some of these in order to achieve a certain desirable characteristic in our system. So let's assume A and B are fixed, and C is variable. So that's as messy as we can get, probably. So let's say A is equal to, I don't know, 4. Notice I'm being really sloppy with units. I haven't assigned units to anything. But these would have units in real life. Since we don't have a situation in mind, none of this has meaning yet. We don't know what units things are going to have. So just use your imagination. All right. So we want to choose C. B, let's say, is I don't know. Let's come up with a value for B. Well, let's stick with 4 is working. Sure, why not? B is 4 too. Choose C. So I've said that we want to conduct a design, that is, we want to choose a parameter so that my damping coefficient will be a very specific value. All right, so this is pretty abstract, right? But this is not unreasonable, right? This happens. Engineers actually have to do these kinds of calculations. Okay, so the very first step, before you even think about how to approach calculating C, right? Don't even think about it. The very first step is put the system in canonical form. Don't try to formulate a solution. Don't start writing equations. No, stop. Put it in canonical form before you forget and make a goofy mistake. Canonical form is this. So we have to get rid of this coefficient. No problem. We can do that. Just divide the whole thing by 5a squared. Notice that I've deliberately chosen things, so these coefficients are not nice, right? They're messy. That's okay. Oh, that's not a double dot. No, silly. And this is 1000 C. This comes out pretty nice, actually. So that's just 200 C squared divided by A squared. How kind. X is equal to 0. Lovely. So let's see how tricky this turns out to be. So I've designed a problem to be about as tricky as we can get it. So now we set these equal. So 2 zeta omega n. Now notice I have not specified omega n. We don't know what that's going to be. Is 14b over 5a squared. And then omega n squared is going to be 200 c squared divided by a squared. Okay, so which variables can we affect? Which variables are available to us to design? C was the answer, right? So we've got B and A are specified. Presumably the other aspects of the design mandate that they be certain values, so we're stuck with just playing around with C. Okay, that's fine. Now I've specified what zeta needs to be, but there's no C here. So it at first glance it looks like, wait a minute, I can't affect zeta with C. Well, yes you can, because C affects omega n. So, okay, we're just going to have to deal with that being an indirect effect. No problem. I can substitute in for omega n. I guess if I had been thinking a little further ahead, I could have made this a nicer square root, but oh well. Life goes on. So, let's rewrite that. That's going to become zeta is equal to, that implies zeta is equal to 7b divided by 5a squared omega n, which is, well, let me isolate omega n. I'll do that as a separate step. Omega n then is just the square root of 200 is going to be 14.14. And that's just C over A. That was not a mistake. I did actually deliberately choose C and A so they would have nice square roots. All right, so we throw that in here, and life gets not bad, right? So it's just the A's are going to cancel. So we plug that in, and we should be left with 5 times 14.14 times A times C. Cool. Well, this is easy. Just solve for C. I'm going to plug in my values for A and B. And I'm going to plug in my value for zeta now. My value for zeta was 0.5. There we go. Force cancel. Let's see. That's 1.4. So that's roughly, let's see if I can do this without the calculator, just for fun. So that's roughly 0.1. I'm going to say that's 0.05. All right, let's see how I do with the calculator. Just for fun. All right, so that's 7. Oh, we'll do it the long way. 7 times 4 divided by 5 times 14.14 times 4 times 0.5. Oops. So maybe I goofed up, because I get 0.198. All right, let me think back through my math. What did I goof up? 7 divided by 5 should be 1.4. Pretty sure about that one. Divided by this is about 0.1. 0.1. Oh, yeah, idiot. 0.1 divided by 0.5 is 0.2. Not 0.05. Yeah, silly. That's where I screwed up. Silly. All right, but we've got C. Can't win them all. All right, so we've got a value for C. Lovely. Now let's go ahead and calculate the other parameters. So now that we've got C, let's figure out, all right, so now so what are the other second order characteristics? So we've said that zeta, the damping ratio, is 0.5. That means the system is underdamped. It will ring, it will oscillate, but we still don't know at what frequency. We still don't know how long it's going to oscillate. And we don't know its natural frequency, right? Which is kind of a measure of the system's speed. More than frequency. It's a measure of the system's speed. So let's start there. Omega n, we actually have an expression for. Omega n, now we got this from the relationship. We said omega n squared was 200. Just to recap, right? Remember, omega n squared was 200 c squared over a squared, right? Which led us to conclude that, all right, omega n and we can just plug in, no problem. So C was about 0.2, and A is about 4, so that should be about 0.05. So that's about 0.0707, I think. Whoops, and I forgot to rewrite my. Or 7.07 rather. Sorry. 7.07. Or no, I'm sorry. Man, I'm all over indecision today. I think that's actually, yeah, I think that's 1 over the square root of 2, 0.707. Let's find out. Clearly, I can't convince myself of anything today. Yeah, so I get, when I actually plug in those numbers, I get about 0.7. So, yeah. Ish, when I round. Yep. There you go. So omega n is 0.7. Cool. So now let's look at what's left. We need to look at omega d. And that's radians per second. So that should be. Oh, ugh, why is this squared? No idea. Just went a little crazy there. Okay, so yeah, let's see. Square root of 0.75. All right, when I multiply all that out, I get. All right, so from the radical here, I get 0.866 here, or the square root of 3 over 2. Interestingly enough, that's yeah, so that's from a 30, 60, 90 triangle. Should sound familiar. And then here, when I multiply that by my 0.7, I get a damped natural frequency of 0.606 radians per second. Running out of room. Sorry. So yeah, we see a pretty substantial decrease in frequency due to damping, right? So the damped natural frequency is in fact pretty substantially lower than the natural frequency. All right, the time constant, that is a measure of how long will the oscillations last. That we can get this way. Okay, so that's going to be... Yeah, let's just plug it in. Yeah, 2.857 seconds. So again, this is pretty slow system. There we go, 2.857 seconds. Very cool. Okay, we've got it. Those are all of our parameters, and we acted like engineers. We actually selected for a constraint. All right, thanks for watching. Hope this was helpful.